All right, so my digital diary question has several parts. The first part is writing down the Bronsted-Lowry acid-base reaction for I think it's acetamide and hydrochloric acid, HCl. So we know HCl's formula, we know how it looks, but acetamide is CH3 connected to a carbon, double bonded to an oxygen with 2 lone pairs, connected then to a nitrogen with a single lone pair and 2 hydrogens. So that's acetamide. So first we got to find the Bronsted-Lowry equation for it. So we're offered this acid and this molecule here, and this molecule is very obviously a base, because if we were trying to take the conjugate base of both of these, the large chlorine, electronegative chlorine atom can more easily stabilize the negative charge that it receives versus the neutral acetamide when it loses an H, making it have I believe, a negative charge that is less easily delocalized, especially from one of these H's. You can't stabilize it as well because there's not any resonance structures that can happen from there. So what we do is we would write. So for number 1, we write HCl plus CH3CO and H2. Right? And now we determine hydrochloric acid is going to be our acid. We would write its conjugate base, which is Cl minus, plus CH3COH. I'm going to put parentheses around that, and then NH2. And this whole molecule has a formal charge of +1. And I'll go into detail of why I decided to protonate the oxygen and not the nitrogen, and why there's a plus charge. So that's what we're actually going to talk about right now. Now that we're going to do it right after this. First, the second part of this question has me looking for the acid, the base, the conjugate acid, and the conjugate base. So we know that HCl is our acid, and we know that acetamide is our base. So we can easily identify that the acid's conjugate base must be the chloride ion, and the conjugate acid must be the remainder. And this is prevalent by that extra hydrogen from the protonated oxygen that can then be used as acid. So now that we know this, now we can go in explaining the different structures of why we chose to put the hydrogen on the O and not the N. So the first option we could have done, which is the one we did do, is CH3 connected to the carbon, double bonded to the oxygen with a single lone pair remaining, then connected to a hydrogen, connected to the amide group from that carbon, right? So that's the one we chose. And the one we could have done, write the word or right here, CH3 connected to a carbon, double bonded to the oxygen, which still has its lone pairs, connected to its nitrogen, which no longer has a lone pair but has a hydrogen. All right, and now what we know about all molecules, all atoms, everything wants to be at the lowest energy. It wants to approach lower energy. So we have to find which one of these versions has the lowest energy, and that's going to be this one right here, because it has pi bonds where near the protonation point. So that way it can easily be more delocalized between this bond in order to lower the energy of the whole entire molecule. Now this one right here would have the hydrogen here, but it would have a formal charge of plus, and the plus can no longer go anywhere, so it would just stay there. It would be localized. But here you would have a plus up here. Pretend that's next to the oxygen. But the pi bonds can move into electron lone pairs, and then it can cause this to have a normal net formal charge, but then double bond to the carbon nitrogen and give this the plus. So that means it's delocalized around the carbonyl and amide groups of the protonated acetamide. So now we have the structures. We explained why we chose this one and why this one is more likely to appear. The last thing to do is find the we have to find equilibrium. So the equilibrium is going to go to where there's going to be more products or more reactants, whichever side has more by the end of the reaction. In order to know that, we have to know which of the acids, this first acid or the conjugate acid, is stronger, because stronger acids dissociate more. And if they dissociate more, more of their products or more of what comes out of it goes to whichever side it wasn't in. For example, if hydrochloric acid is a stronger acid, it's going to completely dissociate and it's going to go over here, and there's going to be a lot more stuff here happening in the product side than in the reactant side. So we don't have pKa values, which would be a really helpful indicator. However, what we do have is knowledge using the periodic table and how conjugate bases work. So if this is the conjugate acid, we know that if we treat it like a regular acid, this would be its conjugate base. And if this were the acid, this would be its conjugate base. So that being said, the conjugate base right here has technically, I believe, it has more than one resonance structure, however, limited resonance structure. It doesn't have that many, so it might not be the indicator in this case. What we do know is that the chlorine atom is a large electronegative atom, so it stabilizes the negative charge it receives as a conjugate base much better, whereas the neutral acetamide is less stable after losing the hydrogen, making the O-protonated acetamide a weaker acid than hydrochloric acid. So, with that in mind, we can say that the equilibrium shifts towards, you could write shifts, or you could write exists more towards the product side. And this is consistent with practical data and what people have observed. Hydrochloric acid is extremely acidic, and from what I know, the acetamide acid isn't as acidic. Hydrochloric acid usually has a higher pKa, and so therefore it would be the acid of choice, the one that dissociates more. So the equilibrium shifts towards the products. And those are the 4 parts of our questions, right? We needed to write the reaction itself, right? Mind you, they are all aqueous solutions. I could write that in. Right? We wrote which one's an acid, a base, conjugate base, and conjugate acid. And then right here, let me show you what happens here. So this right here becomes a double bond. Now you can't have 5 bonds on carbon, so this one with an arrow goes here to create a lone pair, and that makes it two lone pairs, making it 1, 2, 3, 4. Then bond, 5, 6. The plus is gone here, but now this one has 1, 2, 3. Nitrogen, I believe, was it 1, 2, 3, 4, and then nitrogen needs 5, but so 5 minus 4 is 1, so you got the plus here. So that's why it's delocalized around this. It's that dotted right here. It's a little hard to see. So yeah, we entered which are the structures supporting protonation for the acetamide molecule, and which one is more favorable and why favorable. And then we determined where equilibrium is in the reaction. The equilibrium shifts towards the product side based on the reaction above. All right, thank you.